Hello everyone, welcome to the channel. So in this video I'm going to show you the rapid flood mapping with Sentinel-1 SAR Imagery in Google Earth Engine. So now let's get started. So the floods are among the most devastating natural disasters worldwide, causing widespread damage to infrastructure, ecosystem and human livelihood. So rapid and accurate flood mapping plays a crucial role in disaster management and enabling an early warning and emergency response and damage assessment and the long-term mitigation strategies. So the traditional flood monitoring methods such as the ground survey and optical remote sensing often faces limitation due to the cloud cover, rainfall and accessibility issues during the flood events. In this context, the synthetic aperture radar imagery has emerged as an effective tool for flood detection and mapping because of its ability to penetrate the cloud and operate independently of daylight and provides a high resolution backscattered information from the Earth's surface. So the Sentinel-1 mission operated by the European Space Agency provides the C-band SAR data in multiple polarization, for example VV, VH, and the imaging modes, making it highly suitable for the flood analysis. So in the flood mapping applications, the VV polarization is particularly useful because the water body appears as low backscattered regions due to their smooth surface, creating a strong contrast against the non-flooded land areas. So this property allows for the reliable discrimination of flooded zones from the surrounding terrain. So the presented workflow, it's going to demonstrate the rapid flood mapping methodology using Sentinel-1 SAR data in Earth Engine. So with the case study, we're going to focus on the Chennai flood event in 2015. So the approach, we're going to use the cloud computing GE to the Earth Engine to process the large SAR data efficiently and eliminating the need for heavy local processing. So the study area, we're going to first define our region of interest around Chennai and its surrounding, where the flood events caused a severe socio-economic and environmental impact. So we're going to start with the defining of a region of interest, and after that we're going to cover the months before and after the flood events. Since the Sentinel-1 imagery is affected by speckle noise, so the focal median filter is applied for the speckle reduction to enhance the image quality and improve the classification accuracy. So the two SAR composites are to be generated for the pre-flood scenario as well as the post-flood scenario. So by comparing this backscattered intensity between the two time frame, significant changes associated with the surface water indentations are highlighted. So the change detection analysis is performed by subtracting the post-flood backscattered value from the pre-flood image and followed by a histogram analysis to determine the backscattered variation. So we're going to apply a threshold value for greater than 5 decibels is applied to identify the flood areas, and further we're going to apply the binary flood mask is generated, and this mask is going to highlight only those areas with a significant backscatter reduction representing likely the flood affected zones. So now let me get back to Earth Engine. So in our first step, we have to define our region of interest. For example, I have navigated to my study region where the affected flood areas happened. So this is my study area, so where the flood events take place in 2015 here. So to create your own region of interest, first we're going to navigate this option called draw a rectangle. So once you did that, we're going to draw a rectangle over the study region. And once you did that, in the next step we have this new variable called geometry appears in the top section here. You can able to see that. So once you created our new study area, the new variable appears called geometry. So we're going to click this top section called show generated code. So from here I'm going to copy this latitude and longitude of newly created study region, and I'm going to copy this and I'm going to paste it inside this variable called the variable boundary chords. So I'm going to paste it here using Ctrl V in my keyboard. So once you pasted the latitude and longitude of the study region, so the next step we're going to create we're going to convert this variable into a polygon. So to do that, we're going to create another variable called study area equals to earthengine.geometry.polygon. So it's going to convert this variable containing the latitude and longitude into a polygon. So using earthengine.geometry.polygon, and we can refer this particular variable boundary coordinates. So you can able to see that now it's going to convert it into a polygon. So in the next step, we're gonna center this particular layer. So to do that, we're gonna mention map.center object and study area. It's gonna represent over this particular variable with a suitable zoom level. So once you created your study region of interest, so the next step we can move on towards to fix our analysis period. And also you can include your shapefile into this analysis. For example, I'm gonna show you that. So navigate to this option called assets section here. So in the assets section, we have different shapefiles here, so you can able to see that. For example, I'm interested in specific this particular shapefile called study area LS. So it's going to represent the Chennai. So I'm going to click this and show you the shapefile here. So this is the shapefile here. So I'm going to use this particular shapefile for my analysis. So I'm going to import this shapefile. So to do that, I'm going to click this option called import into script. So once you did that, in the top section, it appears a variable called geometry. So we're going to replace the name as a study area here. So it's going to refer this particular shapefile, project Earth Engine, and as its study area LS. So for my analysis, I'm going to use this shapefile. So it is your choice. Either you can use your shapefile for analysis, or you can use this rectangular polygon for your analysis. So for now, we're going to use my shapefile here. So I'm going to delete this particular one here. So in the next step, I'm going to mention my time period of my analysis, for example. So I'm going to define a variable called start year equals to 2015, and end year, I'm going to mention the variable called end year equals to 2016. So now we have fixed our analysis period, and in case if you are using a shapefile, make sure to remove this set of codes here, so it won't be required for in case you are using a shapefile. So for example, in my case, I'm gonna use it as a shapefile here. So I'm gonna turn this off. So I'm not gonna use this set of codes here. So I already have my shapefile which is indicated here. I no need to turn this rectangular coordinates into a polygon. So in the next step, we're gonna load our Sentinel-1 SAR imagery into our Google Earth Engine. So now let me explain about the SAR imagery. So Sentinel-1 SAR GRE C-band Synthetic Aperture Radar ground range detected log scaling. So the dataset availability is from 2014 to 2025, and the dataset provider is European Union ESA Copernicus. And using this code, you can access the SAR imagery, that is Earth Engine Image Collection Copernicus S1 GRD. And this is the short description about this dataset. For example, the Sentinel-1 mission provides a data from dual polarization C-band synthetic aperture radar instrument at 5.40 GHz C-band. This collection includes C1 ground range detected scene processed using Sentinel-1 toolbox to generate a calibrated orthocorrected product. The collection is updated daily, and new assets are ingested within 2 days after they become available. And let me get back to this band section here. So we have 4 different bands that is available in the SAR imagery. For example, HH band, that is 10 meter resolution, and the unit is in decibels. And HH is the single copolarization horizontal transmit and horizontal receive. And HV is a 10 meter and dual band cross polarization horizontal transmit and vertical receive. And VV is a single copolarization vertical transmit and vertical receive. And last is the VH. It is dual band cross polarization, vertical transmit and horizontal receive. And all this band has a unit of decibels, and the resolution is around 10 meters. So now we're going to get back to Earth Engine. So to access our Sentinel-1 SAR imagery, first we're going to define a variable called S1 after equals to Earth Engine dot image collection Copernicus S1 GRD. So in the next step, we're going to filter it based on our region of interest. So to do that, we're going to apply this function called dot filter bound study area. It's going to refer our shapefile here. So it's going to refer this particular variable study area. That is our shapefile. And we're going to filter it based on our study region. And the next step, we're going to filter it based on our time period of our analysis. So to do that, we're going to mention dot filter date, start year, and end year. And then the next step, we're going to mention the calendar range. So for example, this particular flood event has took place during December 2015. So for that, I'm going to mention fix this particular the calendar range December. So I'm going to mention dot filter Earth Engine dot filter dot calendar range 12 start month and the end month. So 12 indicates the December, and the month, the unit is in month. And the next step, we're going to use the what kind of band we're going to use. So the kind of polarization we're going to use. For example, we're going to use the VV polarization, vertical transmit and vertical receive. So to select the transmitter receiver polarization, I'm going to mention dot filter, earth engine dot filter dot list contains the transmitter receiver polarization equals to VV, that is vertical transmit and vertical receive. So this filter, the Sentinel-1 image collection to include only those images that contains the VV polarization in their metadata field called transmitter receiver polarization. So in the next step, we're going to filter it based on the instrument mode. So the instrument mode is the interferometric white swath. So the IW mode, the standard mode for land ocean coverage. So it captures a wide area of 250 kilometers swath with the high spatial details. It is ideal for tracking. So it is ideal for tracking the open water areas. So let me get back to Earth Engine. So for that, we're gonna use the instrument mode to be interferometric white swath IW. So we're gonna filter it dot filter Earth Engine dot filter dot equals to the instrument mode is equals to IW, that is interferometric white swath. And the next step, we're gonna select the suitable band. So for example, we're gonna select the VV band, which is vertical polarization. So to select this particular band, I'm gonna mention dot select VV band. So let me show you that. So we're gonna use this particular band called VV with the units of decibels, and the resolution is 10 meters, and it is a single copolarization, vertical transmit and vertical receive. So why we are using this particular VV band? Let me explain that. So the Sentinel-1 is the C-band synthetic aperture radar satellite operating at 5.4 gigahertz wavelength. So unlike the optical satellites, the Landsat and Sentinel-2, the SAR does not capture the reflected sunlight. Instead, it transmits the microwave signals and measures the backscattered from the Earth's surface, that is how much energy is returned. So the most important aspect for flood mapping is the kind of polarization we're going to use. For example, the VV is a vertical transmit and vertical receive. So the radar sends the vertically polarized microwave and measures the vertical return. So the behavior, the stronger response from a smooth horizontal surfaces like soil or a bare land, and weaker responses from the water, which typically appears in dark. And uses, so VV is highly sensitive to water bodies because the water surface acts like a mirror, sending a radar energy away from the sensors, resulting in lower backscattered. So it provides a clear contrast between the flooded and non-flooded areas, and best for detecting the open waters like river, lakes, and large flooded plains. And in case we are using VH, that is vertical transmit and horizontal receive, the radar sends the vertical polarization but measures the horizontal return. So it is more sensitive to vegetation and rough surfaces, and useful for detecting flooded vegetation because the water under the vegetation lowers the backscattered compared to the normal condition. So it provides the complementary information to VV. While the VV picks up the open water, the VH helps confirms the indentation beneath the vegetation. For example, the flooded agricultural fields or the wetlands. And next typical band is the HH, that is horizontal transmit and horizontal receive. So it is not standard in Sentinel-1 but common in other SAR missions like Radar Sat, and it is similar to VV but responds differently to roughness. So detecting the rough flooded surfaces, less common in Sentinel-1 since it primarily provides VV and VH. And HV is a cross polarized similar to VH, used for vegetation and complex scattering. And using the VV band is the most common in the flood studies. So it detects the open water flood clearly and good for the urban flood monitoring, and simple threshold methods of pixels with so here is mentioned some threshold, but we have to adjust the threshold according to the study area here. So next is the VH band. So it is better for flooded vegetation where the VV might miss the water beneath the tree plant canopy, and helps reduce the misclassification of the dark surfaces like shadow, the bare soil or smooth asphalt that may resemble some water in VV. And why Sentinel-1 is ideal for flood monitoring? So it works day and night. An active sensor, not dependent on sunlight, so it penetrates the cloud and rain. Unlike the optical sensors, the high spatial resolution of 10 meter is ideal for urban and rural flood monitoring, and frequent revisit of 6 to 12 days with Sentinel-1A and 1B, and free and open access via Copernicus and Earth Engine. So VV is best for detecting the open flood water, and VH is best for detecting the flood beneath the vegetations. And using both VV and VH improves the accuracy and reduces the false positive and provides a comprehensive picture of the flood extent. So let me get back to Earth Engine. So now we're going to select the VV band here. So to select VV, I'm going to mention dot select VV. And the next step, I'm going to mention dot map reduce speckle noise. So we have to apply this the speckle noise filter here. So let me explain this. The speckle noise reduction function, we're going to create a speckle noise reduction function. So Sentinel-1 SAR data generally contains a speckle noise, so we smooth it using the focal median filter. So to do that, first we're going to define a function called reduce speckle noise and image. We're going to refer our Sentinel-1 SAR imagery, and inside the loop we're going to return the image dot focal, and we're going to apply this function image dot focal, apply this function on the image dot focal median, and here we're going to mention the radius and the unit and the kernel type here. So the radius is 100 and the unit is in square, and the kernel type is going to be in meters. So the radius is 100 and the kernel type is square, and the unit is in the meters. So first one is going to represent the radius, followed by the kernel type, and next is a unit. And we're going to mention the copy properties to copy the metadata property of this image to this after applying the noise reduction speckle noise reduction function. So to copy those, they're going to mention dot copy properties image dot property names. And once you did that, we're going to refer here using dot map reduce speckle noise. So we're going to refer this particular function here. So this is the function reduce speckle noise we are referring here to apply the speckle filter function. And the next step, we're going to mention the dot minimum function to get the minimum value composite. So now we're going to add our after flood SAR image to the map. To do that, we're going to mention map.addLayer S1 after, referring to this particular variable, and we're going to clip it based on our region of interest, that is study area, and with a minimum value of -25 to a maximum of 0. And last, we're going to output the layer name as after flood. And in the next step, we're going to load our Sentinel-1 SAR data. So we're going to perform the before flood analysis. So we're going to perform the similar steps as mentioned for the S1 after. So we're going to define a variable S1 before flood event. So equals to Earth Engine dot image collection Copernicus S1 GRD. And similarly, we're going to filter based on our region of interest dot filter bound and referring to our study area. And we have to mention the start and the end period of our analysis. So we're going to mention start date equals to the start year, it's going to be 2015, and the end year, it's going to be 2016. And next, we have to fix the calendar range. So if we're going to fix this particular month, so the flood was happened during 2015 December. So we're going to mention the calendar month to be October. So the before flood image. So we're going to mention dot filter, Earth Engine dot filter dot calendar range, start month and the end month, it's going to be October, and the unit is in the month. And next, we're going to apply the filter based on our transmitter receiver polarization. So that is it's going to be VV, that is vertical polarization. So to mention that, we're going to mention dot filter, Earth Engine dot filter dot list contain the transmitter receiver polarization is VV. And the next step, we're going to select the instrument mode. So we're going to select this particular instrument mode, that is IW, interferometric white swath. So to do that, we're going to mention dot select Earth Engine dot filter dot equals to instrument mode is equals to IW, that is interferometric white swath. And next step, we're going to select the VV band. So to select the VV band, we're going to mention dot select VV, that is vertical polarization. And we're going to apply this particular function, that is the noise reduction function. So we're going to mention dot map reduce speckle noise. So this function we early created. So in order to reduce the noise in the SAR imagery, so specifically we applied this focal median filter. So to do that, to reduce the noise, And then the next step, we're gonna add our the before flood SAR imagery. So to do that, we're gonna mention map.add layer S1 before dot clip based on our region of interest, that is study area, and we're gonna set the minimum to -25 to the maximum of 0. And last, we're gonna output the layer name as before flood VV, that is vertical polarization. So the next step, we're gonna calculate the change detection based on the before flood versus after flood image. So in order to calculate, we're going to mention variable flood change equals to S1 before dot subtract S1 after, and we're going to rename as flood change using dot rename function. So now let us visualize the result, the before and after imagery. So we're going to navigate to the top section and click run. So once you click that, we're going to navigate to the layer section here. I'm going to turn on this after flood as well as the before flood image. So now we are currently visualizing the before and after flood image here. So this is the before flood image and this is the after flood image. So you can clearly able to distinguish all the dark patches which indicates the water presence of water. So all these which indicates the water body presence in the study region. So you can able to see with this is the one of the river here, and you can able to see different lakes. And before flood event, this was the condition of water in the study region, and after the flood, it is the condition of water bodies in the study region. You can able to see here a lot of water has been increased in the study region here. So several lakes has been regenerated. You can able to see that a lot of lakes here, and certain areas you can able to see from this after flood image here. Certain areas affected by this flood here. So towards the northern part of the study area has more flood events has taken place here. So you can able to see, I'm going to turn this on. You can able to see the difference here in the northern part of the study region. So this is the northern part of the study region, which is lying in Ennur. So you can able to see, which is here lying in Ennur. So people around the Ennur has been severely affected by this flood during in that time here. So in the next step, we're going to calculate the change detection based on the before and after flood events. So for that, we define this variable flood change is equals to S1 before dot subtract S1 after, and we're going to rename as flood change. And to add this layer, we're going to mention map.add layer flood change, referring to this variable here, and we're going to clip it based on our region of interest, that is our study area, using dot clip function study area. We're going to mention the study area inside to clip it based on our study area, and we're going to mention the minimum and maximum value and the color palettes here, so white and blue, and the flood change map. We're going to output the layer name as flood change magnitude. So now let us take a look at this particular layer. I'm going to navigate to the layer section. I'm going to click this option called flood change magnitude. So you can able to see the flood change magnitude here. So from this image, you can able to see all the blue areas which indicates the change detection. So changes before and after flood. So white area which indicates the before flood situation, and blue area which indicates the changes after the flood event. So you can able to see the difference based on this image too. So in the next step, we're gonna plot a histogram of change value. So we're gonna plot the histogram and visualize the backscattered values here. So to do that, we're gonna mention print ui.chart.image.histogram. So we're gonna refer the flood change variable here. So I'm gonna refer to this particular variable, and I'm gonna mention the study area with the resolution of 30 meters. And additionally, we're gonna set this additional options to this chart. For example, using dot set options title, I'm gonna mention this flood change histogram, and the h-axis, the title is going to be the backscattered change in dB, that is decibels. And let us take a look at this here. I'm going to click this option called run. So let us take a look at this chart here that's going to be generated here. So our histogram is got ready here, so you can able to see the value range of values. So the value starts from minus 3.25 to a positive value here till 5.5. So you can able to see the values here. So it's up to the value. So this much here the value is. So the value ranges from minus 2.75 to this amount. So let us visualize it. So now we can able to clearly visualize the histogram. So I can able to clearly visualize the values here. So value ranges up to plus positive 11.75 to a negative of so a negative up to minus 3.5. So let me now get back to our Earth engine here. So here I'm gonna zoom into this here, the study area. I'm gonna use my inspector tool. So now I'm gonna place my cursor over this water body here, and let us visualize the value here. So after flood, the value is around minus 17.44. So before flood, it was around minus 19.44, and the flood change, which indicates so it is minus 1.75. And similarly, I'm gonna place the markers over this point here, and let us visualize the value here. So the flood change magnitude, the value is around positive 11.8, and similarly I'm going to place the cursor over here. So the value is around positive 11.33, and I'm going to apply some suitable threshold. So a suitable threshold to detect the flooded areas. For example, from the histogram value we have, I'm going to select the values which is greater than 5 here. So we're going to select all the pixels if the value is greater than 5. The decibels values is greater than 5 decibels, and select those pixels to be classified as a flooded areas. So to do that, in our next step, I'm going to apply a threshold to detect the flooded areas. So for example, we're going to apply this specific condition. The areas with value greater than 5 decibels change 5 decibels, we're going to classify it as a flooded areas. So for example, I'm going to mention a variable flood threshold is equals to the flood change referring to this variable, and I'm going to give it a condition dot greater than 5. So once we apply this condition, next we're going to add this layer. So I'm going to mention map.add layer, the flood threshold referring to this variable, and we're going to clip based on our region of interest, that is study area, and the color palette we're going to give it as a blue, and output the layer name as flood threshold mask. So now let us visualize the layer here. I'm going to navigate the layers, and I'm going to turn on this layer called flood threshold mask. I'm going to turn off all other layers. So I'm going to now click this option, and I'm going to select the custom section to be stretched 90%, and I'm going to click apply. So instead of palette, let me select the gamma, and I'm going to click apply here. So now here you can clearly able to visualize the changes here. The flood changes, all the flooded areas are clearly highlighted in the white colors here. So you can able to see that. So all the darker black areas which indicates the non-flooded areas, all the white areas which indicates the flooded areas. For example, in this region the occurrence of lake is quite low here. So in this area I can able to see a lot of flood has taken place here. So which is lying here in Ennur. So you can able to see this areas have a flood event has taken place. So you can able to see this areas here. So you can able to see the white patch which indicates the flooded areas. And let me turn to a satellite mode here, and I'm gonna adjust the transparency. So you can able to see here, so this particular white patch here, so which is lying over the build-up area here, you can able to see that. So clearly these areas has been heavily flooded, and similarly towards this part of the area, so you can able to see, so this area has been flooded, and also this portion has also been flooded, and you can able to see a lot of urban areas has been flooded during this year 2015 here. So you can able to see this flood areas. A lot of rainfall has been taken place during this particular year in 2015. So we can able to see the differences here. So let me change the transparency of this layer here. I'm gonna change the transparency back to normal, and in the next step we're gonna mask the flooded area. So basically we're gonna extract all the flooded areas only. So to do that, we're going to mention a variable flood only mask equals to flood threshold, referring to this variable, and we're going to mention dot update mask, and we're going to mention as flood threshold. So now it's going to give us only the flooded areas and except only the flooded areas. And let us take a look at this. So we're going to navigate the layers, and before that let us calculate the area. And to calculate the flooded areas here, we're going to mention another variable, flood pixel equals flood pixel area is equals to flood only mask, referring to this variable. And we're going to mention multiply earth engine dot image dot pixel area function, and we're going to divide it by 1:10 power 6 to convert from a meter square to a kilometer square. So for that we mention dot divide 1:10 power 6. So to calculate the flooded area, we're going to mention a total variable total flood area equals to flood pixel area, referring to this variable. And we're going to apply dot reduce region, and reducer is going to be earth engine dot reducer dot sum function. So it's going to sum up all the areas of flooded regions, and the geometry is going to mention the study area, and the scale I'm going to mention as 100. And last we're going to mention dot value. So in order to get it as a value, we're going to mention it as dot value, and dot get 0 to get the first value out of it. So we have mentioned dot get 0. And last, to visualize this total area, we're going to mention print estimated flooded area in square kilometers, and earth engine dot number total flood area, so referring to this variable, and dot round, we're going to round it off using this particular function called dot round function. And let us run this code here. Again, I'm going to click this option called run, and let us visualize the result here. So in the console section, we have the estimated flood area in square kilometers, to which is around 66 square kilometers of area. And in the next step, we're going to add some visualization parameter to our layer, that is to visualize the flooded areas only. So for that, we're going to mention another variable. So we have mentioned another variable called flood vis. So we're going to apply the visualization thing to our flooded area. So we're going to define a variable flood vis equals to minimum of 0 and maximum 1, and color palettes white and dark blues, and dark blues which indicates the flooded areas. And last, to add, we're going to mention map.add layer flood only mask, and clip it based on our study region using .clip function, and refer the visualization parameter flood vis, referring to this variable containing visualization parameter, and we're going to output as detected flood areas. So we're going to run this code here, and let us visualize our result here. So in the layer section, and I'm going to turn off all of the layers, or I'm going to turn on only the detected flood areas. So you can able to see this is detected flood areas in the study region. So let me turn to a satellite mode here. So you can able to see all the blue patches here, which indicates the flooded areas in the study region. So you can able to see that, and you can clearly able to visualize it. So all the blue areas which indicates the flooded areas here. So you can able to see a lot of areas with flood affected by this particular area. So occurrence of lakes also pretty low in this towards the northern part of the study region, but you can able to observe a lot of blue patches which indicates the flooded areas. And even in the satellite image you can able to visualize it. So in this area, that is Manali, and also near Ennur and Attipatti, you can able to see a lot of flood that has been happened here, and also this portion of the study region. So in this video I have shown you a rapid flood mapping with Sentinel-1 SAR Imagery in Google Earth Engine. So thanks for watching, and make sure that you subscribe to our channel and give us a like. And the code link will be available in the description section of this video. So thanks for watching.